Okay, so we did this slide last week, the collision model, and we watched this video. Remember the movie? No, you were sick. So it talks about what the significance of these factors is. And so if we think about the frequency factor for a reaction in which we have two gas phase reactants, here, what are we even looking at? A plus B. So the three red balls is the A, and the blue and the red is the B. And in order for those to react, first of all, they have to run into each other. If they never come in contact with each other, no reaction can occur. So they have to run into each other, and they have to run into each other with enough energy in order to react. So each approach to the activation barrier is the collision between reactant molecules. So every time they collide, that's an approach. So the frequency factor is the fraction of times that it actually works. Why is that frequency factor usually less than the number of collisions per second?
Because every time it collides doesn't necessarily mean it's going to react.
Right. Some of those collisions do not have enough energy, so they bump into each other, but it's not good enough. And so that's why the frequency factor is less than the number of collisions per second. So the frequency factor actually has two pieces in it. It's the orientation factor and the collision frequency. The orientation factor the orientation factor is the fraction of collisions with favorable orientation. And so they have to have enough energy, they have to run into each other, but they also have to be aligned correctly. And so the orientation factor tells us that. That's going to be between 0 and 1. The collision frequency is the number of collisions per unit time. That's a very high number. It's like 10 to the 9th per second, because in the gas phase, these particles are moving very quickly and they bump into each other a lot. So we can take the Arrhenius equation, K equals this frequency factor times e to the negative EA over RT. We can take this A out and separate it into two factors, the orientation factor and the collision frequency, P and Z. And we're not going to do a lot of calculations with this. It's more of a conceptual thing about why is that important. So here, if we look at these two molecules, NOCl and NOCl reacting with each other. In order for them to react, they have to collide with the correct orientation. And so here we have illustrated two ineffective collisions and one effective collision. So here, the chlorine atoms in these molecules have to bump into each other. When the chlorine ends bump into each other, a bond can form between the two chlorine atoms. That's where the Cl2 comes from. And then what's left of those two molecules is the NO. If they run into each other and they bump the oxygens, or they bump an oxygen to a chlorine, you're not going to get a chlorine-chlorine bond that forms, and so no reaction will take place. So that orientation factor for this one happens to be 0.16, which is pretty small. Yes?
Is there a reason why those two molecules would decide to would actually pair up and make a new molecule?
Yes, it's very complicated though. Yeah. So you can't just take any molecule and say, well, if one of them runs into another, then they'll react and form something else. A lot of compounds are stable, and so even if they run into each other, they're not going to react. And so this is not necessarily typical behavior. Has to do with energy, ultimately. Yes?
And do they just collide at random, or
Yes.
are they like actively trying to attract to each other?
They are just random. They're not setting out to do anything. They have no intention. There's nothing directing them. They're just little balls floating through space, and they go in a straight line till they bump into something. Now, as they're moving, they may be like rotating or spinning, just depending on how they ran into the last thing. Yeah. Anybody else have any questions? So if we have a small orientation factor that's closer to 0, that means the molecules have to be aligned in a very specific way. When we have reactions between atoms, that orientation factor is usually approximately 1 because atoms are spherically symmetric. If you have 2 red spheres and they bump into each other, does it matter how they're oriented? It does not, because they're the same no matter how they're turned. So when you have 2 atoms running into each other, they're always going to be at the correct orientation because they don't have sides, right? What's really kind of trippy is that it's possible for the orientation factor to be greater than 1, and that would indicate that an actual collision isn't necessary. What? That's just bothersome. Like they don't actually have to collide. They can still react. So weird things can happen. That's all that's saying, really. Okay, so what sort of question might you have to answer on an exam? Okay, because that's really what you want to know, right? Yeah. So something like this, you should definitely be able to answer. Which reactants do you expect to have the smallest orientation factor? So first of all, we have to remember what the orientation factor is, and what is a big factor and what's a small factor. What do those things mean? The orientation factor is a fraction indicating how many of the collisions are in the correct orientation, right? Going back to this, the fraction of collisions with a favorable orientation. So if it's high, that means that almost all of them are going to be lined up right. If it's small, close to 0, that means that most of them are not going to be right. So then we look at these different reactions here. So the smallest orientation factor says that this is going to be something kind of complicated, right? That it's not going to line up very well. So if we look at the first one, we have 2 atoms colliding, and they're going to have a frequency factor that's, a collision factor. That was backwards. Orientation factor that's close to 1, right? Because they're symmetrical. And then we've got this H2 and the I2. Is that going to be closer to 1 or closer to 0? Probably closer to 1, right? Because this molecule of 2 hydrogen atoms, well, it's a hydrogen atom at each end, and so there's not a whole lot of orientation going on. Here we have HCl with HCl, right? And so you have more opportunities for incorrect collisions. Looking at the products here, I think you need to collide so that the hydrogens hit each other and the chlorines hit each other. If you're hitting hydrogen to chlorine, it's probably not going to work very well. So that's going to give us a smaller orientation factor. So it should be that one. Yes?
I kind of missed this part, but if it's closer to 0 or closer to 1, does that make it more favorable and less favorable?
Yes, closer to 1 is more favorable.
Okay.
That means that how they're running into each other isn't going to affect the rate or the rate constant. So it's always going to work. And if it's small, that means that the reaction is not going to go very well because you have to get these things lined up just right. I suppose you could think of it, I'm working on an analogy in my head here, and we'll see if it comes out very well. So if I'm dropping these objects and trying to get them to fit into a tube, so this This is a round tube so the sphere can go into it, and this is a rectangular opening so that can go into it. If I drop this one and just have it hit the right spot, it's going to go in, right? If I drop this one in the right spot, but it's twisted to the side, it's not going to go in. Does that make sense? A little bit like, like Tetris or something. This doesn't matter if it's turned any direction, it'll still fit because it doesn't have sides. This, if I turn it one way or the other, it's just not going to work. And so this you're going to have to drop a lot more times randomly until it fits in the hole. Whereas this will fit every time, if that helps. Yes?
There will always be at least some sort of orientation factor. It can never be zero, correct?
If the orientation factor was 0, that would make the rate constant 0, which means that the reaction would not occur at all. So it really, we would never talk about something that's actually 0, because then we start talking about things that don't happen. And where do you stop when you get into that? We don't want to go there. Any other questions? So that's the answer.